our team. Thank you.
Welcome to the first in a series of events celebrating CERN's 70th anniversary. So my name is Clara Nellist, and I am a particle physicist here working on the ATLAS experiment at CERN. And it's my pleasure to be the moderator for this event. So tonight we will hear from 4 distinguished speakers, each covering different scientific topics, reflecting on the developments of particle physics over the last 70 years, and specifically here at CERN, and also highlighting the huge mysteries that we still have in physics. So we will take a journey through particle physics, starting from what we are well acquainted with, and diving into phenomena that we have still not yet fully understood. So we will discuss antimatter, which is mostly missing in the universe, and also dark matter that exists, but we don't know what it's made of. So to start us off, we will have a video summary of CERN's scientific achievements in the last 70 years.
Everything in our universe is made from fundamental particles. Its immensity is filled with microscopic mysteries. For 70 years, CERN scientists have been working to unveil its secrets, making it the world's largest center for particle physics. At CERN's foundation in 1954, scientists were trying to come to grips with the plethora of particles observed in nature. They lacked an overall framework to explain these basic constituents of matter and the forces that act upon them. This framework would later become known as the Standard Model. Studying the infinitely small meant building experiments the size of monuments.
À Mérin, près de Genève, se trouve le plus grand chantier que l'Europe ait jamais vu. Il s'agit de la construction du Centre européen de recherche nucléaire.
In 1958, the SC, CERN's first accelerator, showed clear evidence of a rare particle transformation, the anomalous pion decay, which had been predicted by the theory but never observed. The PS first accelerated protons in 1959, becoming the world's most powerful accelerator.
Cette machine circulaire accélère des protons, des noyaux d'atomes d'hydrogène, leur imprimant une vitesse voisine de celle de la lumière, environ 300 000 km par seconde, et pouvant leur impartir une énergie maximum de 28 000 millions d'électronvolts.
In 1973, the Gargamel bubble chamber, which received a muon neutrino beam from the PS, proved the existence of weak neutral currents. This major discovery solidified the foundations of the early Standard Model of particle physics.
Les chambres à bulles conduisaient la communauté à laquelle j'appartenais à avoir chaque année 10 millions de photographies à analyser.
In 1968, George Charpak developed the multi-wire proportional chamber, which revolutionized particle detection, heralding the electronic era.
Le prix Nobel de physique de l'année 1992 vous a été décerné pour votre invention et développement de détecteurs de particules.
In 1972, strong interaction between quarks was revealed in CERN's first proton-antiproton collider, the ISR.
The ISR was the first hadron collider ever built and operated.
The SPS was switched on for the first time in 1976. It was then transformed from a one-beam accelerator into a proton-antiproton collider.
l'Académie royale des sciences de Suède a décidé d'attribuer le prix Nobel de physique 1984 conjointement au professeur Carlo Rubbia et au docteur Simon van der Meer pour leur contribution décisive au grand projet qui a conduit à la découverte des particules de champ W et Z, médiateurs de l'interaction faible.
The Large Electron Positron Collider, LEP, was the largest scientific instrument ever built, and its tunnel, Europe's largest civil engineering project.
One of LEP's most important results was an extraordinary measurement of nature's deep properties, the existence of exactly 3 families of quarks and leptons, crucial for understanding the deeper workings of our universe. The size of the LEP collaboration was many times larger than any previous experiment. This created the need for a new universal way of exchanging data among physicists, setting the scene for the invention of the web. In 1995, at CERN's Lear facility, for the first time scientists brought together antimatter particles, forming the first atoms of antihydrogen. In the year 2000, CERN announced the observation of a new state of matter known as quark-gluon plasma. This state of matter prevailed when the universe was only a billionth of a second old.
We have a discovery. We have observed a new particle consistent with a Higgs boson. As a layman, I would now say, I think we have it.
I would like to add my congratulations to everybody involved in this tremendous achievement.
This year's prize is about something very small that makes all the difference.
In the wake of this groundbreaking discovery, the LHC's quest for knowledge deepens, unveiling particles that defy convention and challenge our understanding of the subatomic world. With unprecedented precision, the LHC delineates the Higgs boson's identity, probing its mass, spin, and the subtle ways it influences other particles, seeking signs of new phenomena. We peer into our universe's dawn through quark-gluon plasma, recreated in heavy ion collisions. Yet, the universe keeps its secrets. As the searches for supersymmetry, dark matter, and hidden dimensions continue without definitive proof, but ever advancing the frontiers of physics. As we stand on the brink of tomorrow, the LHC's legacy paves the way for the next generation of accelerators.
We believe very firmly that to continue this search in the unknown, we will need a much larger accelerator at a much higher energy.
The journey is far from over.
Well, that's given you a taste of what we will be discussing this evening. And to start our event this evening, we will learn about the emergence of particles and fields in our universe. And I'm pleased to introduce Dr. Gian Giudici, apologies, who is head of theoretical physics here at CERN, to explain this to us. Welcome, Gian.
Particle physics is not about particles. Today, the alphabet of the particle physics language is not based on particles localized at a point, but on extended entities that fill the entire space-time, called quantum fields. So quantum fields are the building blocks of the current theory of particle physics. Fields are entities that spread everywhere in space and time, but when observed at microscopic distances where quantum mechanics rule the world, fields reveal a point-like nature made of individual quanta. These individual bundles of energy are what physicists call particles. So we can think of particles as waves of an immense ocean, the field. So just as waves cannot exist without the ocean, because waves are manifestations of the ocean, so particles cannot exist without the field, because particles are manifestations of the field. And the concept of quantum fields explains why, for instance, all electrons are perfectly identical. Electrons can exist in different points of space, can travel with different velocities, but their intrinsic properties are exactly the same. All electrons are perfect clones. Why? Because they are simply manifestations of a single underlying entity, the electron quantum field. And the language of quantum fields reveals a wonderfully coherent and unified picture of all natural phenomena. All electrons that exist in the universe today, all electrons that ever existed in the universe and that will ever exist in the future, are described by a single mathematical quantity, the electron quantum field. So quantum fields also achieve the perfect unification between matter and forces. According to quantum field theory, there's no distinction between what exerts a force and what feels a force. In nature, deep inside, there's no matter and force, but fields, only fields. And yet, when we consider the processes that occur at CERN colliders, we talk about particles, not fields. Why? Because we are probing nature at distances that are so small that we become sensitive to the individual quanta of the fields. And a collider such as the LHC is a powerful microscope able to resolve the quantum nature of fields. The LHC dives into the depth of space and sees nature not as a continuum, but as single particles smashing against each other and creating new particles. And this is why when we deal with the LHC, we talk about particles, not fields. But there are situations in particle physics when the full field structure emerges. And one interesting example is the universe itself. Let me try to explain why. There is a special situation in which particles can arrange themselves in a collective structure that forms a uniform field distribution everywhere in space-time. Superficially, you may think, well, there's nothing extraordinary in this. After all, we are all familiar with the existence of electric and magnetic fields that permeate space. But here, I'm talking about something much more surprising. Electric or magnetic fields always identify special directions in space. And if you move with respect to a static electric charge, you see an electric current. Therefore, if you move with respect to an electric field, you see a magnetic field and vice versa. So instead, here, I'm talking about something completely different. A field that looks identical no matter how you turn it or move with respect to it. In other words, a field that is completely indistinguishable from empty space, from nothing. Something that may seem invisible. And yet, it contains some form of energy. And this is what physicists call vacuum energy. So vacuum energy is part of the fabric of empty space-time. It is like nothing, but it's not nothing. Vacuum energy has a remarkable property. Every form of matter or radiation that we know of gives rise to an attractive gravitational force. So, for instance, gravity makes things fall on Earth. It keeps the Earth in its orbit around the sun. It keeps stars bound inside galaxies. But vacuum energy is an astonishing exception. It gives rise to the magical property of repulsive gravity, gravity in reverse. And this may be the secret behind some of the biggest mysteries in the origin of the universe. Physicists believe today that the expansion of the universe started from an initial kick by the vacuum energy reverse gravity, repulsive gravity. And the expansion driven by vacuum energy is so furious that it stretches space to an unbelievable degree, creating the geometry that satisfies exactly the Euclidean rules, those that you have studied in school. Moreover, quantum mechanics generates tiny variations in the vacuum energies that then are stretched to astronomical distances by the fury of this repulsive gravity. And these tiny energy variations are the seeds that after billions of years of gravitational collapse grow into the galactic structures that populate the universe today. In other words, the sky is a portrait of primordial twitches of a quantum field. A quantum field lies at the origin of our universe. And nature makes recurrent use of the extraordinary properties of fields and particles during the history of the universe. About a tenth of a billionth of a second after the Big Bang, another dramatic event takes place in the universe. And the protagonist is again a quantum field. It is the Higgs field, which undergoes a phase transition, suddenly filling the universe with its own vacuum energy. And the story of how physicists reconstructed this spectacular event that occurred 13.8 billion years ago has much to do with the past history of CERN, the past 70 years of CERN. 1973, the Gargamel collaboration using a bubble chamber at CERN announces the first detection of neutral current events. This has to do with the weak force, which is one of the fundamental forces, and it's the force which is responsible for making the sun shine. Gargamel gave the confirmation that the weak force exists in a previously unknown version, where particles do not change their electric charges in the process of exerting the force. And this was evidence that the weak force may come together with electromagnetism in a unified structure and in a single force, which is what today we call electroweak. 1983, the UA1 and UA2 collaborations working at CERN's proton-antiproton collider, the SPS, announced the discovery of the W and the Z bosons, the particles that induce weak interactions. And this discovery confirms that the symmetry structure at the basis of electroweak unification. 1996, 4 experiments working at CERN's electron-positron collider lab measure the interactions between W and Z bosons. And this measurement confirms the hypothesis that the vacuum energy of a quantum field is the explanation for the apparent conflict between mass and symmetry properties in weak interaction. 2012, the ATLAS and CMS collaborations working at CERN's proton collider LHC announced the discovery of the Higgs boson, the particle which makes up the vacuum energy previously identified by Lapp. This was a decisive and final missing piece of the puzzle of weak interactions. It was a path to discovery that lasted about 50 years from the first theoretical hypothesis to the final experimental confirmation, and a path to discovery in which CERN took a leading role. Now, was the Higgs discovery the last word in how quantum fields shape the history of the universe? Not really. Astronomical measurements have revealed that about 5 billion years ago, which is very recently in cosmological terms, another form of vacuum energy has started to become significant in the universe. And this is the so-called dark energy, which accounts for about 70% of the current energy budget of the universe. What is it made of? Is it another quantum field which must be added to the list of the known particles? We do not have an answer yet. Quantum fields have still much to reveal about the cosmological evolution and about the fundamental laws of nature. Quantum field theory, that is the theory that describes particles in terms of quantum fields, is one of the greatest achievements of human intellect. Combining quantum mechanics with special relativity, it revealed the deep relationship between the microscopic world of particle physics and the properties of the universe at the largest possible distances. Fields and particles expose a profound unity of nature in the infinitely small and infinitely large. And yet, in spite of its extraordinary success, we have good reasons to believe that quantum field theory is not the final language in which nature has written its fundamental laws. The language of quantum fields starts sputtering nonsense when gravity becomes relevant in the quantum regime, as it happens, for instance, at the core of a black hole, or possibly at the origin of the universe. In this regime, quantum fields fade away into other structures still unknown. And most likely in this regime, even the concept of space and time evaporate into a new form of quantum reality. There must be something radically new in the depth of space, which we must understand in order to crack the remaining mysteries of the universe. And the path to discovery has no end. And to continue this exploration, one thing we are sure that is absolutely necessary: CERN, for another 70 years or much longer. Thank you.
Thank you so much, Jan, for that incredible overview.
Thank you.
Let's give him another round of applause. So now we move from fields to focusing on the very structure, the internal structure of the proton. And it's my pleasure to welcome Professor David Gross, who is the Nobel laureate in physics for 2004. So welcome, Professor Gross.
Thank
David. So could you give us a snapshot on how atomic theory evolved into the groundbreaking discovery of the nucleus, and what impact this had on our journey into the world of subatomic physics?
Well, the idea that everything, all matter, is made out of point-like constituents, atoms, goes back to the Greeks. But it's only within the 20th century that it was possible to try to understand what are atoms made of, what is the structure of the various atoms that we're made out of. And the real breakthrough happened about 113 years ago by Ernest Rutherford, who figured out how to explore the structure of objects as small as atoms, which cannot be seen in microscopes. What he did, was try to understand what was going on inside the atom by taking a beam of alpha particles, which actually are the nuclei of helium atoms, and bombarding a gold foil to see what gold atoms are made out of. And by observing the deflection of the alpha particles from the gold atoms, he was able, with the help of theory of electromagnetism, alpha particles are charged, the atom contains electrons, presumably something else with positive charge. He deduced that the atom was mostly empty. There were electrons, of course, but at the center of the atom was a very, very small nucleus, which contained most of the mass and all of the positive charge of the atom. He also invented this method of probing the structure of atomic matter and subatomic matter that we still use today. CERN, for example, tries to study what particles are made out of, what matter is made out of, by smashing protons together and seeing what comes out. We really haven't perfected, well, we have perfected, but we haven't conceptually gone beyond Rutherford's method. What Rutherford discovered was a planetary model of atoms. The nucleus at the center, electrons revolving around it, which, by the way, led within roughly 10 years to the development of quantum mechanics, which is at the heart of our understanding of fundamental reality, as well as discovering the nucleus itself. Rutherford's method we still employ today at CERN and at other laboratories, and of course, it's become much more evolved. We scatter protons on protons here at CERN at extraordinarily high energies, and we detect them with extraordinary complex and amazing detectors, but it really goes back to Rutherford.
So here we can see the number of different colliders that we have at CERN, starting with the SC that you can actually visit here at CERN, and then the Large Hadron Collider, which is operating. And so these accelerators are used to explore the forces and also the particles that we have. So in exploring these forces that govern our universe, could you explain the specific role of the strong force for exploring the heart of atoms? And what have been some of the pivotal moments and discoveries that have shaped our understanding of this tiny world?
Sure. So, by the beginning of the 20th century, it was realized that there are many forces acting in the universe. The traditional forces, starting with Newton's first theory of a force, that was the universal force of gravity that acts on all objects that have energy or mass, explains the motion of apples and planets. Very successful theory. In the 19th century, we understood the theory behind the force of electricity and magnetism that acts on charged particles like electrons that carry electric charge and source the field that we just heard about that transmit the force between these particles and whose ripples of the field constitute waves of light and radio waves. And in quantum mechanics, the particles that these fields can be described as are the photons that transmit the electromagnetic forces. In the 20th century, after Rutherford's discovery of the nucleus and the structure of the atom, the goal was to understand the forces that exist within the nucleus. This was not easy. The nucleus is 100,000 times smaller than the atom, and it wasn't until the middle of the century that we could start exploring the nucleus, protons and neutrons that make up nuclei experimentally. And it was understood by then that there were two forces acting within the nucleus. One was the weak force that we heard about. That we now understand as the force that changes one kind of quark, which I'll get to in a moment, into another kind of quark, is responsible for radioactivity, for the transmutation of elements.
And it's also responsible for our sun shining as well.
Many
we could
good
not live
things
without
as
it.
well as radiation. But the hardest force to understand was the so-called strong force, the force that held the nucleons together inside the nucleus and was responsible for whatever was going on inside the proton itself. Much like what was the atom made of, we now are asking, what is the proton made of?
So why was it so difficult to study the strong force?
Well, in the case of the other forces, say electromagnetism, the sources of the fields that in field theory and in quantum field theory give rise to these forces was evident. You could, J.J. Thomson in the 19th century discovered electrons. You could see electrons. You could knock them out of the atom, make them go in wires and power our motors. But in the case of the nuclear force, we learned that the constituents of the proton are in fact things called particles that one had never seen in the laboratory, called quarks, with very strange properties. Fractional electric charges. No one had ever seen such objects. So nobody really believed in the idea of these quarks, whose existence was hypothesized to explain the mathematical patterns of new protons, neutrons, strongly interacting particles that were being produced in the accelerators here at CERN and elsewhere. So it was very hard. You couldn't see directly the constituents of the proton. They were hidden. The pivotal experiment took place on the other side of the world in Stanford at the SLAC Stanford Linear Accelerator, which actually reproduced the original Rutherford experiment. What they did there, in essence, was to scatter electrons, which are simple point-like particles, off protons to try to see what the proton was made out of, much like Rutherford scattered alpha particles off gold nuclei, atoms. And what they discovered, and were awarded the Nobel Prize for discovering quarks, was that the proton looked like it was made out of point-like particles, which had all the properties, the rotation, the spin, and the other properties of quarks, these hypothetical mathematical objects. And remarkably, when observed in these experiments, these quarks, these point-like particles, seemed to move freely around as if there was no force acting on them. Well, that was an amazing discovery, but for a theorist like me, it was crazy. Because how could it be that there were these quarks moving around freely inside the proton, and yet you couldn't pull them out? You couldn't ionize the proton. And that eventually led us, after many attempts, to find a theory in which this phenomena was explained. Phenomena we called asymptotic freedom. And it is a property of a generalization of Maxwell's theory of electrodynamics. Electricity and magnetism, there's one kind of electric charge. In quantum chromodynamics, there are three charges. We call them whimsically colors: red, blue, green. And those colors source a field, just like the electromagnetic field, except because there are three colors, the field is more complicated. The carriers of the force, like the quanta of radiation, photons, in the case of quantum chromodynamics, there are 8 carriers. We call them gluons, because they hold the quarks together.
This is one of our better named particles.
Yes.
Gluons that glue them together.
And the remarkable thing about this theory is that, contrary to your natural intuition and what everyone always expected, this force becomes weaker and weaker when the quarks are closer and closer together. That's asymptotic freedom, which explains the experiment, which found that, discovered that phenomena. But it also, conversely, if you pull the quarks apart, it gets stronger and stronger, which could explain, and we believe it does, why no one has ever produced a quark in the laboratory, at ordinary temperatures at least.
So unlike an electron, which we can isolate, these quarks are not, we can't get them on their own.
Unfortunately, we can't. It would be very interesting if we could knock quarks out of the proton and make them travel in wires and do all sorts of wonderful things. But we can't. They're, under normal circumstances, confined within the proton. And this is a picture, an illustration of 3 quarks, different colors. By the way, these 3 colors, red, blue, and green, add up to white. That's hard mathematics, so I won't try to explain it. But the proton as a whole has no color, which is why the force between protons and neutrons, the nuclear force, which is pretty strong, which is why atomic bombs are so much more powerful than TNT, is still weak compared to the force between the quarks. It's sort of a molecular force compared to an atomic force. Anyway, here the quarks are exchanging gluons, and this force is so powerful that if you try to pull a quark out of the nucleus, what happens, you can't. The force just continues, does not decrease, so it becomes energetically possible, and this is what happens. You pull an antiquark and a quark out of the vacuum. You have enough energy to do that, and the proton splits into a proton, which is colorless, and a quark-antiquark pair, a meson, which is also colorless. So if you hit a proton like at CERN, quarks don't come out. You can see them at short distances, but they never come out.
So we get this spray of hadrons in our detectors, and we call these jets, which we will touch upon later. So then how does this look within our sort of recipe book of the rest of the
Well,
the
this was the Higgs. Aside from the Higgs, this was the final building block in understanding both the constituents of matter and the nature of the forces that act at subatomic and subnuclear levels. And the standard model is illustrated here with the list of basic elementary constituents, quarks, 3 families of quarks for reasons we don't understand, and 3 families of accompanying electrons and their friends, the neutrinos, which we call leptons. They actually fit together very nicely, a very important clue that all of the forces of the Standard Model are at some point unified. We still don't understand how that works. As well as the 3 forces that act on these particles: electromagnetism, explaining atomic theory and the structure of atoms; the weak force, which changes quarks, one kind of quark into another, electrons into neutrinos; and the electromagnetic force, of course, and the strong force that binds the quarks together into nuclei.
So some might say, well, this is interesting, but what is it good for? And how would you respond to a question such as that?
Well, so that's a kind of question that reporters often ask. What is this good for? Well, of course, it's most importantly good for understanding how the world works, answering the curiosity that children have. What is the world made of and how does it work? But we have learned that every advance in fundamental physics eventually has implications that change our world. Quantum mechanics has led to the discovery of the laser, the transistor, has totally changed our world in ways that the inventors never imagined. So who knows? Maybe in 100 years, 200 years, we'll know what the implications, what it's good for in the sense of technology and economics. But when fundamental advances occur in basic fundamental physics, they often affect other branches of science. And the one that was immediately affected by the development of the standard theory, the Standard Model, was our ability to extrapolate the history of the universe way beyond the cosmic microwave background, which was observed in the 60s and was an indication that the Big Bang theory of the universe was the right way to look at cosmological history. So astrophysicists and cosmologists wanted to understand what happened before the cosmic microwave background. That was 300,000 years after the Big Bang. And you can't observe directly beyond that at earlier times, but you can extrapolate the theory. And before the Standard Model, that would be impossible because you didn't know how atoms and nuclei behaved at the extraordinarily high densities and temperatures of the early universe. As you go back in time, the universe gets denser and hotter.
And so how does it look when we go back in time?
Well, we understood quite immediately after the discovery of asymptotic freedom in QCD, quantum chromodynamics, that if you take nuclear matter and squeeze it, it gets denser, the quarks get closer together. If you go to very high energies, the quarks have much higher energies, which means that the relevant distances are smaller, and that's where asymptotic freedom comes in and says, okay, the quarks don't interact. So what was conjectured was that at high temperatures and high densities, ordinary matter, nuclear matter, would undergo a phase transition to a different phase of matter. In effect, the protons would melt, and quarks and gluons would come spewing out, forming, at very high temperatures or high densities, what we call the quark-gluon plasma. Well, that was a prediction, if you want, of quantum chromodynamics. And if true, could enable cosmologists and astrophysicists to extrapolate the universe back to the very beginning. Amazingly, this transition was discovered and seen here at CERN 24 years ago, where we recreated a very dense and hot fireball by colliding two heavy nuclei with lots of nucleons, lots of quarks together at very high energies. And as you can see here, that fireball cooled off rapidly, but before it cooled off, the nucleons melted, the quarks came out, and there were signs of a new state of matter, a fascinating new state of quark matter, nuclear matter, which is still being investigated and understood.
It's incredible that we can recreate these conditions similar to the early universe. So also reflecting on the extraordinary work with the Large Hadron Collider, which you touched upon, how has this program influenced our understanding of the theories that you have discussed?
Well, the LHC played, as we've heard in the previous lecture and my lecture, an enormous role in developing the Standard Model and testing it, finally, more importantly, with the discovery of the Higgs boson. And it continues to do so. There are 4 detectors at the LHC. 2 of them, ATLAS and CMS, enable us to directly test with extraordinary precision the Standard Model, especially QCD. They're very precise experiments. And the other, ALICE and LHCb, probe the quark-gluon plasma and discover new kinds of quark states. So, as an illustration, the primary feature of the strong interactions, the strong nuclear force, is this phenomena of asymptotic freedom, pictured here. This line that's falling as you go to higher energy or shorter distance is the decrease of the strength of the strong nuclear force. And that's now tested in literally dozens of experiments with precisions better than 1%. That's how we are convinced that our crazy theoretical ideas are probably not wrong. Nature never tells you, by the way, that you're right, but it often tells you that you're wrong. And if it says, okay, you're not wrong this time, many, many times we begin to believe in the Standard Model, which really should be the standard theory.
We'll update our textbooks.
Other measurements of, for example, the production of these jets, sprays of nucleons, protons, pions, strongly interacting particles that one sees in the LHC detectors, enable one to go back to the original collision and see the quarks themselves and how they're moving. And those quarks can't come out. They attract other quarks to form these protons and neutrons, sprays of hadrons, which are what you observe, but with the help of the theory, you can extrapolate back and see actually the quarks colliding and producing particles. The agreement illustrated here between theory and experiment is unprecedented, and it assures us that the theory is correct, and it enables us to look for new physics. If we truly understand with great precision the old physics, then we can look for new physics, such as the Higgs boson. Theorists, of course, also can test theories by calculating things that the theory predicts. For example, the masses of all these particles, the proton, the neutron, the pion, the kaon, the dozens and dozens of strongly interacting particles that are produced at colliders. And they have masses. And now we can calculate, again, after 40 years of trying, Lattice QCD has been able to calculate these masses to better than 1%. This whole story requires unbelievable technological advances. In the case of theory, that's also the case. To be able to calculate these masses to 1% required an improvement of 18 orders of magnitude. 9 of them came from Moore's law, the development of modern computers. 9 orders of a factor of 1 billion. The other factor of 1 billion came from new algorithms, new understanding of the physics of QCD. All in all, 18 orders of magnitude. And now we can do these precise calculations. Finally, the other 2 detectors at CERN probe, for example, new quark states, new states, bound states of quarks. The proton is made out of 3 quarks. Pions are made out of quark antiquark. But LHCb has now discovered many new quark states. Still, we don't totally understand them, including evidence for states made out of 4 quarks or 5 quarks, 5 pentaquarks. And of course, Alice, having discovered the quark-gluon plasma in the laboratory, is now studying in great detail the properties of this very strange and interesting new state of matter, which existed very early on in the universe, but also, we suspect, might exist at the center of neutron stars, where very dense stars, where the density is so large that, again, nucleons can melt into quarks and gluons. And we now have the possibility of observing that new state of matter in neutron stars by the gravitational wave signals that occur when neutron stars collide and merge and produce ripples in gravity.
So we've covered a vast amount of physics. So to sum up, from your perspective, what aspects of future research in particle physics are you most excited about?
Well, so my whole career has largely focused on trying to get clues from nature through my experimental friends who do experiments at CERN and elsewhere by probing to shorter and shorter distance. So I'm very excited by the possibilities of new machines for new knowledge, of extending our reach by at least an order of magnitude, both at the plans here at the CERN for the high luminosity LHC, which will increase the number of collisions by an order of magnitude, and even more so eventually, maybe not in my lifetime, but by the FCC, the proton-proton collider at 100 TeV. There's so many questions that, I discussed the successes of the standard model, but they're great mysteries. Dark matter, which John discussed, the matter-antimatter asymmetry in the universe, the strange spectrum of quarks and leptons that we don't understand. There are so many wonderful mysteries, and likely surprises that will be discovered by these machines. So I'm thirsty for that knowledge. And as Rutherford would have said, onward and onward.
Excellent. Thank you so much, David.
Any questions?
So thank you for that wonderful summary of the structure of the proton and also on what we're going to be looking for in the future. Exceptionally, we're going to take 2 questions from the audience. So I believe we have somebody with a mic who will be, so we have the first question over here on the right.
Hi, thank you for the talk. As a theoretical physicist, how do you feel about the fact that we've had this big discovery with the Higgs boson in 2012, but since then, we've been thinking about things like dark matter and supersymmetry, but no one really knows what is the truth of nature or what is just a theory. How do you feel about that?
Well, there are people who have criticized CERN or particle physics for not discovering what some theorists have told them they should have discovered. And it is important to remember that when science explores new territories, new energies, like with the LHC, it's an exploration. It's like it's territory that no one has ever ventured into before. So we have ideas what might happen, suggested by clues. For example, astronomers have discovered dark matter throughout the universe. One possibility, most likely, is that consists of some kind of heavy particle that doesn't interact strongly with us. And therefore, it's hard to detect. So we've been searching for it underground and in the galaxy and trying to produce it in accelerators and still haven't succeeded. Okay, good. We've learned a lot. Dozens and dozens of possible explanations. Theoretical ideas have been ruled out by not discovering what might have been there. So we've gained an enormous amount of knowledge. The same is true of supersymmetry, which still might be there at higher energies. It will be discovered by high luminosity LHC or by the FCC. We learn as much by asking nature a question and nature saying, it's not there yet, or nature saying your idea is wrong. That is incredibly important to the development of science, as important, sometimes even more important, than discovering directly a new phenomena. The famous experiment of Michelson and Morley, looking to measure the velocity of the Earth through the ether, which everyone believed in, existed and permeated the universe, they discovered no discernible velocity, which Einstein interpreted as no ether, and that led to the theory of relativity. So it's just as important not to discover what some people think must exist as it is to discover new particles.
Thank you very much.
Thank you. So we have another question in the audience. Here.
I wanted to say thank you for your speech, and then I have a shorter question. What is your dream accelerator?
So now you're asking a theorist, a speculative theorist, what. So I do actually have a dream accelerator. There are particles which we've been looking at forever, since theory of electricity and magnetism, sources of magnetic fields, much like electrons were sources of electric fields. Magnetic monopoles, we call them, magnetic sources. Never been seen. In unified theories that unify the forces of the Standard Model, which we speculate about, there are bound to be such magnetic monopoles. And if the unification happens at very high energy, these magnetic monopoles would be very massive. Now, that actually posed a serious problem for the standard or the unified Standard Model, because no one's ever seen a magnetic monopole. And in fact, the idea of inflation, this rapid expansion of the universe, was invented partially to explain why we don't see a lot of magnetic monopoles. They were diluted by the expansion. So my dream accelerator is that Elon Musk goes to Mars and discovers magnetic monopoles and anti-magnetic monopoles on Mars. And he collects them carefully in magnetic traps, bottles, say, and brings them back to Earth. And we construct a new laboratory, different than CERN. We don't need accelerators. We just have a laboratory with, on one side, a collection of monopoles, which are stable, they don't decay. On the other side, anti-monopoles. We construct an enormous detector, very carefully. And once a day, we bring a magnetic monopole and a magnetic anti-monopole together. Poof, they annihilate. Now, because they're so massive, they could have masses of 19 orders of magnitude heavier than the proton. The energy released in such an accelerator would be 19 orders of magnitude higher than what we can achieve at CERN. So this would be a high energy collision, except we're annihilating particles. Presumably there won't be many of them, so we have to be very careful and do very precise measurements. And that would be a ultimate accelerator whose energy could go up to the scale of unification, close to the famous Planck scale, where gravity becomes an important quantum force. Now that's a dream. Nobody's ever seen a magnetic monopole, but they could exist. Just have to find them. They're presumably very rare, and that's would certainly justify the Mars expedition.
Well, we also have experiments here at CERN looking for magnet. Yeah. We have a couple of experiments looking for magnetic monopoles as well, so we'll let you know if we find any.
Well, I hope they find them.
Excellent. Well, let's thank David again. So as we just heard, antimatter is one of the big mysteries in physics, and specifically, where did it all go? So now I'm pleased to welcome Professor Tara Shears to the stage to tell us all about this topic. So welcome, Professor Shears. Tara, thank you so much for joining me. So antimatter often sounds like something out of science fiction, but it's real and a fascinating aspect of our universe. So could you start by explaining to us what antimatter is and why it's so important in the world of physics, and perhaps touch on why it's so rare?
That's quite a long question. So I'm going to start off, first of all, with matter and what we understand about matter. And we've heard a lot about how we understand matter from Jan and also from David, but I'm going to pick as my starting point our knowledge of matter in terms of particles. So from all of our experiments so far, we have worked out that there are just 12 different types of fundamental particles, 6 different types of quarks that David has just talked about that experience a strong force, and 6 different types of particles called leptons that don't experience a strong force. Now, this is stuff, but what we realized, or what a man called Paul Dirac realized 96 years ago, is that there's another form of matter in the universe, antimatter. Now, this came about because Dirac was operating in the very first days of quantum theory, trying to develop ways to explain the motion of electrons. Now, electrons are very small, so you need to use quantum theory to describe them, and they can go very fast, so you have to combine that with Einstein's theory of special relativity. And when Dirac did that, he found two solutions to his equation. One solution, which looked just like an electron, but the other solution looked like an electron that had the other charge. So not a negative charge, but a positive charge. Now, Dirac thought there must be physical reality behind this extra solution. And 4 years later, experimental evidence was found for something that looked like an electron, but was positively charged, the anti-electron. And since then, we've realized that every single type of fundamental particle we know about potentially has an antimatter counterpart, a particle that has the opposite charge and behaves like a mirror version. And when I say a mirror version, that's shorthand for saying it behaves differently under one of the fundamental forces, the weak force that Jan was talking about. Now, we do know what happens when matter meets antimatter. It annihilates, releasing all of its matter as energy. So if I had 1/4 gram of antimatter, which I would not, because it would just simultaneously annihilate with 1/4 gram of me with the explosive force of 5 kilotons of TNT, it would be noticeable. You would be able to tell if you had antimatter around. But we don't. We do not see that happening. And we don't see that happening just because antimatter is really, really rare. Now, you might have mentioned science fiction. I want, as an aside, to assure you that antimatter really is real. And an everyday source of antimatter is a banana. Believe it or not, an average banana will emit 40, that's 40, antimatter electrons every day due to the radioactive decay of an isotope of potassium that it has.
So if someone's eaten a banana today, they are generating antimatter inside of them for a little while.
Yes, but don't panic. It's a very small amount. And there are far fewer antimatter electrons than there are real electrons. You would not notice this.
So, moving to the cosmos, what does the current research tell us about the presence of antimatter in space? And are there any recent findings or experiments that shed light on the large-scale existence of antimatter?
So we've seen that antimatter's rare, but I should say why that's an issue for us. So it's an issue simply because at the start of the universe, when we had the Big Bang, we think at that point half of it was made of matter, half of the universe, but half of it was made of antimatter. And when the fundamental particles and antiparticles that composed the universe at the time met each other, they would annihilate, releasing light that was energetic enough to create more particles and antiparticles. And this process continued as the universe expanded and cooled until eventually, about a second or so after the Big Bang, everything had expanded so much, cooled down so much, lost sufficient energy that this process could no longer continue. And what we are made of here, what everything in the universe we can see is made of the leftovers of those last annihilations. And the reason that we are here is due to the fact that there was very slightly more matter than antimatter at that point in the universe's history. Very slightly more. If it was the same, everything would have cancelled out. Everything in the universe would just be light now. So if we want to understand why we're here, we need to understand what makes antimatter that little bit different to cause it to be so rare now. Now, having said that, as you've just very sensibly pointed out, you could think, well, maybe antimatter's elsewhere in the universe where we just haven't seen it. And it's true, it's a really good question. But cosmologists have the answer for us. They've already had a look. And they've used the cosmic microwave background that David has already talked about. So this is the first light that's trapped antimatter, where you might have lots of annihilations with the matter around it. Well, in fact, they don't see evidence for any large patches of antimatter. They don't seem to be there. And even if you sum up all the antimatter that could be there that you're not quite sensitive to, you still get a tiny, tiny amount. There very definitely isn't that much antimatter in the universe. However, that's not to say, I'm getting round to answering your question now. That's not to say that the answer to understanding antimatter's behavior might not be out there. And we have an experiment that is investigating this very question. It's called the Alpha Magnetic Spectrometer, AMS for short. It took off on the space shuttle in 2011. It's now installed on the International Space Station, where it is taking data and has taken data ever since. Now, AMS is a particle physics experiment. It just happens to be out in space. And what it does is measure cosmic rays, these high-energy particles that roam around space. This experiment can identify what sort of particles these are, and crucially, whether they're matter or antimatter. So it counts them up, sends down the data to the control room, which is here at CERN. Now, we do expect there to be a few sources of antimatter out in space. The most boring sort of antimatter occurs when protons are going through the universe and just scatters around in all the dust. And then antimatter electrons are just produced as a byproduct. And if you were to look at all the electrons that AMS has collected, and you were to look at the fraction of that that's made of antimatter, you would expect that fraction to be bigger at lower energies, which is where this scattering becomes effective. But interestingly, you could also have sources at high energies. And this is really what drives the experiment. There can be astrophysics sources, pulsars that accelerate particles to enormous speeds, including antimatter, or potentially certain types of dark matter that when they annihilate, produce antimatter that's very energetic. And that would be something to see. So what does this experiment see? Well, let me cut to the data. This is the actual data, everything that's been released so far. So the points are all the data. It's showing you that fraction of antimatter on the y-axis as a function of energy. And you can see that there are two bumps. One bump at low energies, that's the proton scattering. But intriguingly, another bump when you go up in energy. Now, it might be pulsars, it might be dark matter. We just don't know yet. We don't know. We don't have the precision in our understanding. So AMS is continuing to take data, and hopefully we'll find out more in the near future.
Well, it's very intriguing, and yes, and we'll also learn more about dark matter in the next talk as well. So, coming back to Earth, unfortunately, how do the incredible machines like the LHC here at CERN contribute to our understanding of antimatter, and what kind of experiments are being conducted that help unravel its mysteries?
So far, I haven't actually pinpointed any measurements that show us how antimatter and matter are really behaving differently. And when Dirac came up with his prediction of antimatter, at that point, antimatter and matter were expected to behave in the same way. But there was a bit of a bombshell 60 years ago when experiments in America first found signs that one of the quarks, the strange quark, behaved differently with its matter and antimatter versions. Now, experiments at CERN investigated that afterwards to try and distinguish why that was happening. In 2001, experiments in America and Japan then found evidence that beauty quarks and antiquarks behave differently. This has then been investigated in a way I just talked to about in a moment at LHCb, which itself 5 years ago found the first evidence that charm quarks and charm antiquarks behave differently. So this whole spectrum of difference is starting to reveal itself. And on the lepton side, well, there's even hints that neutrinos may be exhibiting differences between their matter and antimatter versions. Just hints, we don't know. We've got to wait for the next generation of experiments to really find out. So let me turn to how we can investigate this now and what's going on. And I really want to recommend, if you're interested in antimatter, that you come to CERN to study it, because CERN enables us to study it at two levels. The fundamental particle level, first of all, you can study antimatter at this level using the Large Hadron Collider. It's a little-known fact. But when the Large Hadron Collider operates and crashes its beams together, what it's doing in that moment when the beams crash together is it's creating new particles and new antiparticles. It's a really good source of antimatter. And when we build experiments around this collision point, we can take snapshots of what's produced and record it and then analyze it later. And that's what physicists like me do. Now, one of the experiments at the LHC, LHCb, was designed specifically to investigate matter and antimatter. So this is a really lovely picture of the inside of LHCb. So if you're ever lucky enough to go on a visit underground at CERN to see LHCb, normally what you'd see is a lot of scaffolding, because the real detectors are behind it. But if you're lucky enough to be able to go underneath, you'll see the heart of the experiment. You can see the beam pipe, that cylinder.
So this is where the collisions from the LHC, the center of the collisions happen.
At one end. So if you can imagine a beam sort of zipping down this pipe, it's en route for its collisions down at that end. Yes, which is where the business happens. And then particles are produced and then spray in this direction. Now, the key to how LHCb investigates antimatter is that LHC will create equal amounts of matter and antimatter beauty quarks. LHCb then reconstructs these particles by the time they've decayed a millionth of a second later. So by picking a characteristic way these particles decay, so you can identify them in your experiment, you can then simply count how many of them you have that are made of matter and how many of them you have that are made of antimatter a millionth of a second after you knew you started with half and half. This is an example of one of our published results. So this is showing you the outcome of selecting beauty quarks and beauty antiquarks in a particular signature. So matter is shown on the left, antimatter is shown on the right. The big clear peak, that's our signal. The other peaks to the left of it, that's just background, so we don't worry about that for the moment. Now, the point I want to emphasize here is that the scale on the y-axis is exactly the same for both plots. But you can see the height of the matter peak is bigger than the height of the antimatter peak. And what that means is a millionth of a second after we started off with equal amounts of both, we see more matter than antimatter. We are seeing the same sort of thing that we think went on in the very early universe. And this is fantastic because we can measure it. We can measure it with precision, and that means we can investigate it. Now, that's not the only way you can investigate antimatter at CERN. CERN also allows us to investigate antimatter at the atomic level, and it has a really interesting history of doing this. So back in 1965, experiments at CERN and in America for the first time found evidence of anti-nuclei. And then, as we heard earlier, in 1995, CERN created the first antimatter atom, so an antiproton with an anti-electron whizzing round it. And now CERN has built up the technology housed in this wonderful building genuinely called the Antimatter Factory, the best named building ever, I think there is at CERN. And this is full of experiments dedicated to understanding the properties of anti-hydrogen atoms. Now, it's really difficult to do this because how do you keep an anti-atom still for long enough to actually be able to measure it? Well, that's what these experiments do. So they build high-tech atom traps. So they can suspend anti-atoms in a vacuum by means of a magnetic field. And then when you have atoms in one place, you can measure their structure to compare with normal hydrogen. You can see if they fall up or down under gravity. And so far, these experiments see that antimatter atoms and matter atoms behave in the same way to the precision that they've been able to measure so far, although they're constantly developing their challenging technology to be able to search more and to make more precise investigations.
So that's an incredible amount of studies into antimatter. To wrap us up, could you sum up where we currently stand in our quest to fully understand antimatter and specifically this difference?
Yes, so I've shown you many different ways in which we're trying to investigate it, but I think really the best way we have to understanding it comes at the fundamental particle level. And that's simply because we're genuinely able to measure differences and we're able to measure them precisely. Now, there's a bit of an issue in actually working out what it is that we're seeing, because we don't understand why there should be these differences. We don't have a prediction that can explain it. And so what we do in order to be able to try and understand what's going on is we try and incorporate and add on this difference into our theory, so at least it reflects reality. And we do this in quite a straightforward way. We've got one number, just one number, and this stands for the difference between matter and antimatter. And our idea is, if we make a measurement of the difference between matter and antimatter, then we can compare it with its corresponding prediction, where we know everything in the prediction apart from the value of this number. But by comparing the two of them, we can see what value that number must have if these two values are going to be the same. So then we can repeat that for a different type of measurement of matter and antimatter differences and get another estimate for that number. And again, and again, and again. And then we can step back and see if all of these estimates that we've got actually make any sense and are consistent. So let me show you the state of the art in where we've got to. It's a really colourful picture, but do not worry. Each one of these coloured bands is an estimate of the difference between matter and antimatter that we've extracted from a particular type of measurement. Different colours are different measurements. Now, the key here is that all of these coloured bands overlap at one point on this graph. And what that means is there's one value for the difference between matter and antimatter, which, if we put it back into the theory, means that our theory is going to exactly predict all the measurements we've made. It's going to be consistent, and even better, if we then start using that theory to predict other measurements that are related to matter and antimatter differences, we see that they match as well. So even if we don't understand the mechanism for what's going on, we've hit upon a way of describing it. So that must be giving us a clue. Well, we can test that. We can test it by going back to our friends, the cosmologists. They have equations that describe how the universe evolves that just rely on an estimate of the amount of matter, the estimate of the amount of antimatter, and the difference in behavior between them. So we can give them our estimate of the difference between matter and antimatter. They can add it to their estimate of how much matter there is in the universe, wind the clock back on their equations, and work out how much antimatter this implies there must have been at the start of the universe. And when they do that, oh, confession time. They, unfortunately, don't find half a universe's worth like we're hoping they would to answer our questions. Instead, this equates to more like a galaxy's worth. So we have seen a difference, but it is just way too small to explain the question that we have set ourselves. It just does not give us the answer. So this is the state of the art of our experimental knowledge, but this is the state of the art of our understanding. We do not know yet, but we have stepped forward because what we've realized is that the answer doesn't lie in quarks. It might lie in neutrinos. And as I've said, we've seen hints. We have to wait for the new generation of neutrino experiments to come online and take data, which they will be doing towards the end of this decade. Or it might be that the answer lies in completely new phenomena, new mechanisms of physics, perhaps dark matter, perhaps something else even more exotic. And we're really trying to find any evidence of that. But perhaps that is the way forward.
Well, it looks like there's still a lot left to learn about antimatter, but thank you so much, Tara, for your wonderful explanation. So now we move from a substance that is missing in the universe to a substance that we have observed in abundance, but we don't know what it's made of. And our last discussion for this evening is about dark matter. So I'm pleased to welcome Dr. Juna Kroon to the stage to tell us about dark matter. So So welcome, Dr. Krohn. Juna, so dark matter is also a term that captures the imagination of scientists and the public alike. Could you start by maybe demystifying this concept for us? What exactly is dark matter, and why is it such a crucial component in our understanding of the universe?
Well, Clara, I think, if I knew what dark matter was, as nice as this event is, I would not be standing here. I would be frantically writing up the paper. So unfortunately, I can't tell you exactly what it is. But I can tell you quite a lot about it. So we do know quite well, for example, how much there is. So what I'm showing you here is a pie chart of all the energy in our universe, and there's 3 main constituents. And we already heard quite a lot about visible matter, like our ordinary matter. And we have learned so much about that in years and decades of discovery. We've also heard about dark energy, this mysterious substance that seems to permeate all of space and actually seems to push stuff apart, accelerating the expansion of the universe. But then there's also dark matter, and dark matter is actually not all that different from ordinary matter. It also attracts via gravity. The big difference, though, is that it doesn't seem to actually interact strongly with ordinary matter. And what do I mean with that? Sorry, I should actually say, I was talking about how much there is, and I think you can actually guess. I already put the answers for you, so it's probably easy to guess. But actually, what's interesting and fascinating to me that ordinary matter, what we have discovered so much about, actually just is this tiny sliver of all the energy in the universe. The big majority is this mysterious dark energy, but even if you look at all of the matter, 85% of it is dark. So really, there's a very, very big component of the universe, and we just don't know what it is. So why do we not know what it is? Well, it doesn't interact strongly with the stuff that we know. And what do I mean? You and I are made of ordinary matter. And that means that if I look at you, photons can reflect in your skin, and I can see that. And that's how I observe you, and that's how you observe me. If you were made of dark matter, the photons would go right through you, the light would go right through you, and you would be transparent to me.
So perhaps invisible matter is also a good name for this substance.
Invisible matter, yeah, that would be a good name as well. And as you can see in the image, my partner is actually 50% invisible matter. So hence my curiosity.
So it sounds really important then.
So important. Actually, you and I and everyone in this room actually owe our existence to dark matter. And why that is because, in the formation of galaxies, it turns out gravity is really important. And it actually turns out that ordinary matter is not enough to give enough gravity to form galaxies as we know them. So no galaxies, no stars, no planet, you and I. So you owe actually your existence to dark matter, whether you knew it or not. Okay. What I did want to mention as well, within galaxies, we know quite well where dark matter is located. So unlike dark energy, which is kind of permeating all of space, dark matter is localized. It sits in galaxies. Like ordinary matter, there's more of it at the center, but unlike ordinary matter, it extends much, much further out.
So it's fascinating how scientists have gathered evidence for something as elusive as dark matter. Could you walk us through some of the evidence that we have for it? And what are some of the key observations that have led to confirm the existence of dark matter?
I can. We actually have an overwhelming amount of evidence for dark matter, and it's all consistent with each other. We really, really know that it exists. So our story begins in the 1930s with actually a Swiss physicist named Fritz Zwicky. And Fritz Zwicky looks at the Coma cluster of galaxies, the galaxy cluster. And given the laws of physics, you can predict how these galaxies are supposed to move with respect to one another, given their mass. But if you do that, and you try to match that with observations, actually that doesn't work out. And the only way to make it work out is to predict this new form of matter that is not visible with our telescopes. And Fritz Zwicky did that, and he called it dunkle Materie, which is, of course, German for dark matter. So already in the 1930s. Now, a few decades later, Vera Rubin actually looked at the motion of stars within galaxies. So, again, using the laws of motion, you can predict what you expect, how you expect these stars to move within a galaxy. And what you would expect is something like the gray dashed line in this plot, based on the matter that you can see. But that is not what was observed. What was observed is these data points, these little bullets with the error bars. And they tell you a very different story. You see that like the rotation curve, as it's called, it flattens out rather than it tapers off. And the only way to match observation and theory, again, is to predict this kind of new form of matter, dark matter, which extends further out. Now, one really kind of good way of looking for dark matter has to do with how gravity works astrophysically. And this is actually super fascinating. Gravity astrophysically, if there's a very large mass, a very compact, dense mass, it can bend light around it. And how we can see that in the sky is we look at stars, and they can be kind of flattened like a little pancake, or even we can see multiple images of one particular object.
So this is called gravitational lensing.
It's called gravitational lensing, that's right. And then there's different kinds of gravitational lensing. But for example, if you have like a distant object and there's a galaxy that passes in front of it, it bends the light, but it bends the way in which it bends the light has to do with how much mass is in the galaxy. So you get actually kind of it's a way of weighing the galaxy. You get a mass measurement of the galaxy. And again, the only way to make that work out with the matter that we can see in the galaxy is by hypothesizing, this dark matter that sits within it. Now, this gravitational lensing is a methodology that's used so much, and it's used on different scales, and you can even look for particular dark matter candidates using gravitational lensing. Good. Okay. So this one I wanted to mention because it's actually kind of gives you some evidence for particle dark matter specifically, as opposed to changing the laws of gravity. So what you see here is the bullet cluster. And the bullet cluster is actually two galaxy clusters that have collided. And the different types of material that sit in a galaxy behave quite differently when the galaxy cluster collides. So there's the stars. Now, it's actually quite unlikely that the stars collide. So the stars tend to pass right through each other. They're affected by gravity, but they pass more or less right through. But there's a lot of gas in the galaxy, and that actually heats up, and it kind of stays behind. So that's like the pink stuff in this image. And we can see that using, X-ray observations. But then there's also dark matter, and we can infer that using gravitational lensing. And actually, that kind of moves more with the stars. And so you can see the separation of the gaseous matter and the dark matter, here in this image.
So the dark matter has passed right through each itself.
That's right.
And come out the other side.
Because it doesn't interact as strongly, and the gas does, so it's left behind. And now the last thing I wanted to mention, and that doesn't mean that's the last piece of evidence for dark matter, but just the last one I wanted to mention, is again this baby picture of the universe. So this is really the earliest picture that we have of the universe, such a long time ago. But even here we can see evidence for dark matter. So you see the cosmic microwave background, the photos of the CMB, and you see all these little perturbations. So basically what happens is like you have a cosmic fluid, it's sloshing around, and the way that it is sloshing around depends on how much gravity there is. And so that gravity, how much gravity there is, kind of guides like how it's sloshing around and how many blobs you see of different sizes. So we can put that in an image. That's this kind of plot here, this what we call a power spectrum. And it just would look very differently if it wasn't for dark matter.
So we've seen lots of evidence that shows us there is dark matter in our universe, but it seems that there are still many mysteries left to unravel. So what are some of the biggest questions or challenges that scientists are currently facing in the study of dark matter? And what is it about dark matter that keeps you awake at night with curiosity?
Yeah, right. Obviously, at the top of my wish list is what kind of particle is dark matter. So we've seen that the standard model of particle physics, which is all this ordinary matter. There's different kinds of particles, and I would like to know what where dark matter fits in that type of equation. So for example, is it a boson or is it a fermion? So that really guides how it will behave under the quantum laws. Then I say, you know, there's a dark matter particle, but I don't know that. There could be many dark matter particles. It could be 1, it could be 3, it could be 10, it could be 10 million, for all we know, right? You know, 15% of the matter is this ordinary matter. There's all these particles in the ordinary matter sector, you know, it's all this mathematical structure. Who knows whether or not that is the case for dark matter? We don't know. We don't know that. And it would be really fascinating to find that out.
So we could have an entire dark sector of
could
particles.
have an entire dark sector, yeah. There could be so much structure that we don't know about yet. Yeah. Good. So this is an interesting one. So also what we do not know about dark matter, would like to find out, is its mass. So we actually we really don't know. We really don't know. There is about 80 orders of magnitude of mass that dark matter could have. And just to illustrate what that is, between your mass and the mass of an elephant, there's 2 orders of magnitude. Between your mass and the mass of an ant, 7 orders of magnitude. An ant and the whole galaxy, 48 orders of magnitude. So the difference between the mass of an ant and the mass of the whole galaxy, 48 orders of magnitude. That's a large amount, but still not as much as the difference between the lightest dark matter candidate and the heaviest one. We really don't know. Now, all of our matter that we do know, all of the particles that we have discovered, they fit in it like a sliver of this space. And there's some reason to believe that our dark matter could be, you know, not far from there. And, you know, that's obviously where we've looked. But, you know, we have to be quite inventive, and we're actually, you know, kind of trying to probe this full range. Now, then what we also don't know is, does it actually interact with ordinary matter at all? We talked about how it doesn't interact in a way that we have observed yet. But there is reason to believe that maybe there is some sort of interaction that is just around the corner, and we just haven't observed yet. So one reason to believe that, for example, is I showed you that there's about 5 or 6 times as much dark matter as ordinary matter, and that might seem like a large ratio to you. But what I have learned in physics is that it's not a large ratio unless there is something that's kind of protecting the balance, if you will, keeping the balance. The balance is very often very quickly, you know, completely tipped. And so you might end up with like 1 million times more dark matter than ordinary matter. And there's no reason to believe that that's not the case, unless there is some sort of intertwinement in history, in the histories of ordinary matter and dark matter. And that intertwinement would come from an interaction. So we don't know whether or not it actually interacts at all in a non-gravitational way with ordinary matter. Good. And then what I wanted to mention is, what we don't know is what role dark matter played in our cosmic history. So we talked a little bit about our cosmic history with the previous few speakers. So what we don't know is like what role dark matter played. So when was it produced? Was it ever actually part of the primordial soup? You know, if it was a part, when did it stop being a part? And did it ever, you know, kind of guide how the expansion of the universe went? And all sorts of questions like that need to be answered really in the first second of our early universe. We don't have the answer to. Now, it's very hard also to learn about the early universe. And, you know, hopefully we're making some inroads. There's some ideas that are quite, you know, promising for the near future to learn more about that.
Excellent. So how do we then look for dark matter? We have a lot of questions that we still don't know about it, but how are we looking for it in experiments?
Yeah, good. So yeah, as I was saying, you know, there's this incredible wealth of like models and, you know, masses. It's a lot of, you know, parameters that we need to explore, and we need to be quite inventive in how we look for dark matter. So let me just start with kind of a classic way. So one thing that you can do if dark matter interacts weakly with the stuff of the standard model is you bury a tank of noble gas. Because noble gas interacts, it's not very reactive. You bury it underground, just so it's shielded from all of the cosmic rays and all the other stuff that hits the Earth. And then you wait, and if a dark matter particle, dark matter particles can fly through the Earth and fly through your detector. So this should say, on the slide, it should say dark matter, not standard model, but dark matter. If that happens, and it might then interact with like the stuff in your detector, that might give like a little wiggle that, if you have a sensitive detector, could be observed.
And how about in space?
In space, yeah. So another thing that you could do is you could look for signals of dark matter annihilating in space. So what you could look for is, for example, dark matter annihilating, and you could look for the decay products. And one of the ways that you could do that, one of the experiments that does that, we've heard about from the previous speaker, that's AMS. Look for cosmic rays, cosmic rays that could be a signal from dark matter annihilating in space.
So turning our attention to the amazing dark matter research also happening right here at CERN, could you tell us about some of the work that is taking place to further our understanding of it right here? And how are the experiments and technologies contributing to this field of study?
Absolutely, yeah. Good. So at CERN, in particle collider experiments, you could look for dark matter by directly producing it. So if you have a high energy particle collision, maybe you could produce dark matter. Now, that might be quite lucky if that happens, but then the challenge is, of course, how do you detect it? Because it is interacting so weakly, so probably doesn't leave a trace in your experimental, trackers or calorimeters. How do you detect it? Now, one of the ways that you could look for it is, what you look for is missing energy. So if you reconstruct really well all the other particles that you can detect, and you're missing some energy, then you know that something's up. Something must have flown out that you haven't seen. Another way that you could look for it is, there might be particles that actually interact with the standard model and dark matter that aren't dark matter themselves, but they can interact with dark matter. And you could look for those by just looking for a little bump. They could be produced from standard model collision and then also decay visibly, and you could look for a bump.
So it's similar to the way that we discovered the Higgs boson, where we saw a bump in our data.
So
we could look for more bumps in our collisions and see if this could explain dark matter.
And that wouldn't directly tell you about dark matter, but it would tell you about a mediator, which then might lead you on the right track. Good. So two things I still wanted to mention, because there's really kind of a wealth of experiments that CERN is also involved in. They're not all collider experiments. There's also this experiment called CAST. It's the CERN Axion Solar Telescope. It looks for dark matter particles of the ultralight kind. They're really on the far ends of the spectrum of masses that I showed you, axions that are produced in the sun and then could sort of interact here with the magnetic field in the detector, and you could sort of detect them in that way. And another type of experiment that looks for ultralight dark matter is Na64. It looks for dark photons by hitting a fixed target with a beam. And that's kind of a completely different type of experiment that also happened here at CERN.
So these are two dark matter candidates that we're looking for in non-collider experiments.
Right.
And how about the future? What do you see for the future of dark matter research?
Right. I think it's bright. We have so many different ways of looking for dark matter, and scientists are so inventive in inventing more. I think specifically here at CERN, what I would be really excited for is, the future circular collider. We've already heard about this in David's talk. So, in the history of colliders, this is not, Tevatron was not the earliest collider, but just for scale. Tevatron and then LHC, there's already a huge update in how much energy you could probe. With the future circular collider, that would go up again. With more energy range, you could actually detect more particles. So if dark matter just happens to be just beyond reach right now in terms of energy, you could maybe produce at the future circular collider. So that's one way. Another way is looking, of course, again for these mediators, or actually really, really precisely pinning down the interactions of the particles of visible matter to look for tiny discrepancies that give you a hint towards dark matter. So you could look for tiny discrepancies in Higgs physics, for example, to give you a hint. Yeah.
Wonderful. Well, thank you, Juna, for this wonderful overview of dark matter so far, and also a glimpse into the future of our research into this mysterious substance. Thank you so much.
Thank you.
So tonight we have heard from 4 brilliant speakers, and we've looked back over the achievements at CERN and in particle physics more generally in the last 70 years. And we've also looked into the future and the big questions that we still have to answer in the field. So I would like to say thank you again to each of our speakers for sharing their time with us this evening. And I would also like to thank you for joining us on this journey of physics. Before we move to the musical performance, we will close this part with a short video. Thank you very much.
Seul un laboratoire bien équipé attire les physiciens expérimentateurs, évite la dispersion des talents européens et suscite l'apparition des forces latentes.
Sur le plus important chantier suisse à Mérin, près de Genève, le prix Nobel de physique, M. Félix Bloch, a présidé la cérémonie de la pose de la première pierre de l'Institut européen pour la recherche nucléaire. Grande date dans l'histoire de l'Europe. C'est avec fierté que la Suisse, représentée par M. Max Petitpierre, président de la Confédération, apporte sa contribution à cette vaste entreprise. Pour la Suisse, c'est M. le ministre Micheli qui appose sa signature sur un document qui devra permettre une poursuite exclusivement pacifique de la recherche scientifique. Dans la halle qui lui est destinée est installé le synchrocyclotron avec un gigantesque électroaimant. Une collaboration internationale donne à l'Europe la faculté de posséder ses propres laboratoires de recherche.
Le faisceau de protons arrive donc dans le synchrotron par la tangente. La raison de cette disposition circulaire de l'anneau, elle est simple. On veut communiquer aux protons une vitesse proche de celle de la lumière.
Le champ magnétique était un truc qui est petit comme ça, qui est devenu énorme, avec des groupes qui sont immenses.
CERN possesses a unique machine, where beams of protons collide head-on in the intersecting storage rings. High-energy protons brought from an accelerator circle in opposite directions around 2 rings of magnets.
But for the selection of the photographs, nothing can quite replace the eyes of the scanning girl in the hunt for the tracks of the whimsical neutrino.
The structure of the transfer systems T20 and T60 has to be complex in order to make the best use of the 10 to the 13 protons which are accelerated during each SPS cycle.
UA1 has singled out 5 events in a total of 1,000 million collisions, revealing the expected signature of the charged W boson.
This pioneering machine consisted of a string of 5,176 magnets and 128 cavities to accelerate electrons and their antimatter counterparts and guide them into collision at close to the speed of light.
When the World Wide Web was invented, we offered it to the world.
Well, I would like to add my congratulations to everybody involved in this tremendous achievement.
2, 1, remote stable.
As we celebrate CERN's 70th anniversary, we are not just looking back at our achievements, but also gazing forward to a bright future in the coming 70 years and even beyond. We have ambitious goals for compelling projects that should allow us to take giant leaps in our understanding of the fundamental laws of nature.
Inspiring evening we are having with science, discoveries, 70 years of CERN. And now to finish the day, we have a very special performance. It's called Enigma.